generated. So TLP packet is something which takes the your application payload. Let's say you want to access something, write some memory location of your endpoint device. So you will request that you will run some command from maybe dev command, or maybe your driver is doing a IO remap to write something on the memory location of the endpoint. So that will be packaged as part of the TLP, and so this is your data payload in that case, and that will be packaged as part of TLP, and this header will be appended on top of that. So TLP is mainly so after your TLP is mainly packaging your application data and pushing to the PCI stack, you can say. It takes care of all the assembly, disassembly, and basic.
Yes, question. On the CPU side, communication from drivers and applications with PCIe devices is memory mapped always.
Yes.
So you do a read or a write somewhere in memory.
Yes.
And the root bridge will translate that and serialize that into a PCI Express transaction on the bus, like this.
Yes.
Okay.
So, I mean, what will happen is you will do a memory read. That will do. There will be a MMU translation from virtual to physical. That will be pointing to some region in your system memory map, and that is not directly accessible. So there will be on some SoCs there are some address translation units which will translate that address to PCI addresses, which your endpoint device can understand. So what's the root? So as soon as you try to read that in location, your CPU interconnect will notify root complex that okay, someone is trying to access this location, which is not your system RAM, and your root complex will check its own memory information whether this request is within this window or not. If that is within that window, it will initiate a TLP memory request and update the requested address with the new translated address, which is your PCI address, based on the address translation unit we used for the translation, and they send that TLP to the endpoint. So that is how it will do. Okay, so I think, yeah, this also takes care of all the assembly, disassembly of the TLP packets, this layer. And then we have different kind of TLP packets. So this one is for reading only the configuration space of the endpoint. We also have a memory read write, which is to read the actual internal memory of the endpoint, not only the configuration space or the internal registers of the endpoint. And also we have message. So we talked about PCI support MSI interrupts, which is message-based interrupt, not the hardware line. So for that we use message TLPs. And IO read write also, we have different kind of TLPs, but this is the legacy thing. We are not going to cover IO mapping in this slides anywhere. I'm just capturing it so that we know that there are some kind of packets. So this is what TLP is. Now, after TLP, there is another layer which is appended on top of the TLP packet, which is data link layer. It appends the sequence number and the link CRC. So sequence number is mainly used. What it does is data link layer send ACKs for all the packet. So sequence number is used to track whether ACK is received or not. So if you are sending a TLP with a sequence number of 23, let's say, so you should receive a ACK with the same sequence number. It's like a TCP thing. So similar to that. That is what it does. So data link layer takes care of sending ACK and ACK. And also, it also takes care of the flow control. So what it does is on host side and on endpoint device side, we maintain credits, like how much packets a host can send from host to endpoint, and same set of credits will be maintained here. So let's say we have 50 credits maintained on the endpoint side and 50 on the host side. If let's say host is sending 4 bytes of data, which is 1 data word, there will be, so now the updated credit will be 49 because this packet consumed 1 credit. And as soon as this packet is received on the endpoint sends a update FC, which is the updated value 49 to the host. So the host knows, okay, now I can only send 49 packets, 1 is already consumed. So that is what data link layer does. It generates the flow control packets. And then the physical layer. Physical layer is something in this packet, it only appends the start and end, but it does the most important thing. It runs the LTSSM state machine, which decides how many lanes are connected, which we talked about, whether this is a cross 1, cross 2, cross 4 device, how much speed it supports, what's the link width, all these things are taken care of by the physical layer. So I think these are the only 3 layers which PCI support, and we'll be mainly talking about the transaction layer packet because that takes care of all the memory transaction and configuration space transaction. So we already covered some theoretical part. So this is the packet capture from the PCI. So we cannot run a Wireshark kind of thing and just capture the packet. We have to have a separate hardware to capture these kind of packets that sits in between your endpoint and root complex. We have to connect a separate hardware which checks what packets are going. I'm not sure if you're able to see this clearly. No, maybe I'll try if I can. So I think the first packet, this green one, is the config read type 0 packet. What this packet is doing, it is trying to read the configuration space of an endpoint. You can assume maybe a Wi-Fi card which is connected to your PCI system. So it is trying to access the register 0 of the Wi-Fi card, which is the vendor ID and device ID of the Wi-Fi card. So this packet is initiated from the host controller or a PCI controller. So this guy has sequence number 18. And if we see this one, this is the ACK, sequence number is 18. So that is why we use the sequence number in the TLP packets. That's the use of it. ACK also use the same sequence number. And then we have something called tag. Tag is, so here we can see tag is 17. And this tag should be, so whenever we are sending a configuration request, we are expecting a reply from the endpoint with the correct data. Let's say we are sending a request for vendor ID. We are expecting a reply with the vendor ID details. So this was the request. This green one is the reply from it. So tag of both the packets should be same. Then only a host will understand whether we got the correct output or not. So that host knows, okay, I can only send this many packets now. So these are those FC packets. ACK we already covered. This is the completion data. So we requested for the information, we received the information with same tag and same, and I think the most important thing is the data field. So here in the data field, we can also see this shows the vendor ID and device ID of the Wi-Fi card. And these are the requester ID and completer ID, which you can maybe similar to your source address and destination address in the network packet. Requester ID is the source address, which is 0000, because that is the root complex that is connected to bus 0, device 0, function 0. And it is trying to access the configuration space of Wi-Fi device, which is your PCI device, and which is connected after the root port. So it is connected to the bus 1, device 0, function 0. That is why it is showing bus 1 means 00, device 0, and function 0. So I think, yeah, these are the packets we have.
I have a question.
Yeah.
So there's the tag, is it a transaction tag? Or what is the tag? What's the tag used for?
So
is that transaction tag?
yes. So tag is used in combination with the requester details. So whenever, let's say, whenever I'm trying to access some configuration space, I'll put a unique value, which is, let's say, 23, and I'm sending that packet. Now, whenever endpoint is replying with that request, it should put the same tag value in the reply packet. Then only.
It's a request token.
Yeah. You can say that. Yeah.
So does that mean you can have multiple requests in flight?
Yes. You can do that. Yeah.
Sure.
Yeah.
You say like you should send a tag with the data, but you just saying on the previous slide that we are actually using a sequence which to send the data. That's it.
Yeah. So this one is we are sending the request, and this one is the data. We are receiving the data, and yeah.
I mean, the sequence number and tag is not similar. I mean, there are
So this is the tag column.
Yeah.
So when we are sending the request, tag is 17, and when we are receiving the request, tag is 17.
Yeah. Can you go to the previous slide?
Okay.
Yeah.
Yeah.
Yeah. Here we don't see the tag.
Tag is part of this header itself.
Okay.
So maybe I think that I'll cover in maybe another slide. So tag. So this is your TLP header. So tag and other details are part of the header itself. I think I'll be covering that in next slide after the packet capture. Okay, so TLP packets are mainly used to access the memory space and configuration space. We already talked about configuration space. It is a dedicated register space assigned to all the PCI devices, and it is PCI standard, not vendor specific. So we have different types of TLP. These are the three categories of TLP. Posted is something which is not expecting any reply. So it will just send the packet and sits idle. It will not expect for any response. Non-posted is something which is similar to the one which I showed. It will request for data, and then you will expect a packet with the data. So non-posted packet are that kind of packet. And completion is your reply packet, which is coming with the data. So we call that as a completion packet. So there are different categories of TLP, which we can divide it into different types. So memory read is when we are trying to access some location of the endpoint, which is non-posted because we are expecting some data whenever we are reading. Write is something we are just writing, we are not expecting anything. IO read, we are not using anymore, so I can skip these. Configuration read is something we always, configuration read and write are something we always expect the reply, even if there is no data, just for the confirmation that write was successful. Because that is something important whenever we are setting something in the configuration space to enable certain configurations. I think that is must, we should get acknowledgement of that. Message is posted, which is the mainly used for interrupt generation, MSI, and then completion is the reply packet again. So I think then move to the next. Yeah, so this is the TLP header, which I think you were asking about. So I think the first 0th byte of the TLP header define what type of packet it is, whether this is memory read, memory write, IO read, IO write, configuration read, configuration write, completion, or message. So 0th byte define that. And then I think these are the fields, maybe I can skip. I think one important field is this one, which tells whether this TLP is corrupted or not. So this is one of the status field. And then we have, this is the length field. Length field is something which defines or which tells how much data you want to read or how much data you want to write. If you are writing only 4 byte of data, or you are reading only 4 byte of data, let's say vendor ID and device ID, length field will be set as 001. So whenever you are talking about transaction layer packets, you will always talk in units of data words, which is 4 byte. You will not talk about something like 8 bit or 10 bit or 12 bit. So you will always use data words. So there is only one data word is used, which is 4 byte if you are reading only the vendor ID. And same when you are writing something, you will always use 4 byte. Then this value will be set. This is the length. Then this is the requester IP, which is nothing but you can treat it as your source IP address, which is 0000000 because root complex is connected on top of the topology and it has bus 0, device 0, function 0. Now tag is part of the TLP header. So tag is the unique value which is assigned when we are sending the packet, and reply packet also we are expecting the same value. So because there might be a chance we are reading multiple different registers with different values, or maybe different applications are trying to read same register, so there will be multiple configuration requests with same register and same information. So tag is something which will differentiate between those requests.